My name is Susan Arnold, and I am an associate professor at the University of Minnesota School of Public Health and a member of the occupational hygiene faculty. In this module, I will discuss approaches to assessing exposures. The learning objectives of this module are to describe the different approaches that are available for assessing occupational exposures, to examine pros and cons associated with each approach, to summarize the application of measurement data for occupational exposure assessment, and to describe the role of qualitative assessments. There are 5 general approaches to assessing occupational exposure. These are personal and area exposure measurements, deterministic modeling, probabilistic modeling, inference, and professional judgment. Personal and area exposure measurements can be broken down by route of exposure as follows. When assessing inhalation exposures, personal exposure measurements are used to measure the concentration of the chemical or chemical mixture in the air within the individual's breathing zone. The breathing zone is defined as the hemispheric area forward of the shoulders within a 6 to 9 inch radius of the worker's nose and mouth. Area measurements can be used as proxies for personal exposures by accounting for the time activity of the worker relative to the area measurement. Dermal exposure measurements are obtained by wiping the exposed skin, clothing, or surfaces to measure contaminant loading. Wiping an individual's skin directly measures the external exposure, but the complex pathway from surface skin exposure through uptake, absorption, and distribution make it much more challenging to relate these measurements to the internal exposure. Surface measurements serve as an indicator of the potential for dermal exposure. Biomonitoring assesses internal exposure that is the culmination of exposure through inhalation, dermal, and oral exposure. There are several types of sources that can be used, including blood, as shown here, urine, hair, nails, and other sources. Breathing zone measurements can be collected using integrated sampling methods. Active sampling, using a personal sampling pump to draw air at a predefined rate across the sampling media, is a common sampling technique. The pump must be pre- and post-calibrated to produce accurate measurements of the mass concentration. Another option is the use of passive sampling. This technique does not require a sampling pump because it relies on Fick's first law of diffusion to draw air across the filter media. Passive sampling tends to be less expensive than active sampling, making it a popular option when available. Area measurements can augment the information provided by personal sampling. To be clear, area measurements are not substitutes for personal exposure measurements, as they tend to correlate poorly with exposure. However, these correlations can be improved for point sources when they are linked with time activity data. They can also offer important insights about source characteristics and dispersion patterns of airborne contaminants. Area measurements can be collected using direct rating instruments or using integrated methods similar to the integrated personal exposure monitoring. Measuring dermal exposure is more complicated than measuring inhalation exposures. In the figure on the left, a dermal dosimeter in the form of a patch or pad is used to intercept the contaminants that would otherwise deposit on the skin. The figure on the right represents the complex path that chemicals must take from the stratum corneum on the surface of the skin through the epidermis and dermis layers before reaching the bloodstream. Measuring the amount of a chemical on a skin surface provides a measure of external dermal exposure. Using modeling methods, the internal exposure can be estimated by making assumptions about the rate of migration from one compartment to another. Biomonitoring provides an internal measure of exposure or dose, depending on the marker. The biomarker level is a cumulative exposure, meaning it reflects uptake through all routes of exposure. Biomonitoring involves taking samples from biological sources, including the sources shown in the figure on the right, such as blood, urine, sweat, and fingernails. It's a lagging indicator, telling us about the exposures that have occurred in the past. Depending on the chemical in the marker, it may reflect exposures in the very recent past, such as minutes or hours, or it may tell us about exposures that have occurred over months or years. There are several barriers and limitations to making exposure measurements related to the methodology, timeliness, cost, and feasibility. Under methodology, validated methods that are specific to the chemical of interest and sensitive enough to detect exposures at a concentration below the threshold of interest or concern must exist before reliable exposure measurements can be made. Typically, this threshold is 1/10 of the occupational exposure limit. Method development is expensive, costs between $40,000 and $60,000 per chemical, and for complex chemicals, this cost could double. Regarding timeliness, direct reading methods provide near real-time feedback, while integrated sampling methods require that the sampling media be sent to a lab to be analyzed. This extra step can take days or weeks before results are available. The delay in getting results makes it harder to link them to the specific environmental conditions or work practices. Furthermore, if a decision about the acceptability of an exposure is needed immediately or within a few hours or days, exposure measurements may take too long. Regarding cost, the cost of collecting exposure measurements, factoring in the professional's time, equipment, and analysis, is about $2,000 per sample, making cost a significant barrier to making exposure measurements. It also puts tremendous pressure on minimizing the number of samples that are collected whenever exposure measurements are made, creating other challenges associated with small sample sizes. Regarding acceptability, biomonitoring methods are invasive, ranging from less invasive sources such as fingernails or cheek swabs to more invasive methods such as blood. Personal aversion and cultural influences can be barriers to using this method as well. Feasibility encompasses all the factors mentioned here, with one more barrier: access to the site. Many companies are global enterprises with centralized or regional health and safety resources. Reaching a site when it's halfway across the world is a non-trivial undertaking, requires significant time commitments, logistical arrangements, and cost that serve as barriers. Further, in many cases, exposure assessments are needed for processes that are not yet or no longer in operation, making exposure measurements for these situations infeasible. Modeling is an approach that uses key determinants such as the emission rate and ventilation rate to predict exposure under a specific set of conditions. Mathematical modeling is based on physical and chemical properties that allow us to leverage properties that predict behaviors of the chemicals and the impact of engineering controls, such as mechanical ventilation, on the airborne concentration. They are powerful tools that provide the opportunity to consider the impact of changing conditions on exposure, quickly and inexpensively. The freely available tool IHMOD 2.0 can be downloaded from the AIHA website. Deterministic models provide point estimates of exposure. The inputs to the model equations, such as the well-mixed room model with constant mass emission rate, shown here, are represented by single values and produce a point estimate of the concentration at a specific time, or C at T. A couple of examples of deterministic models are listed here: the Structured Deterministic Model 2.0, or SDM 2.0, and box models, including the well-mixed room and near-field far-field models. The Structured Deterministic Model 2.0 is based on 3 key algorithms that require just 3 inputs. The outputs include a point estimate of the 95th percentile of the exposure profile distribution. The algorithms have been refined over many years where robust exposure measurement data sets were available to evaluate them. You can learn more about this model in the module, The Structured Deterministic Model, found on the InTERACCT website under the Chemical Hazard Recognition section. The box models listed here are also based on chemical and physical principles, and when applied deterministically, they provide a point estimate of the 95th percentile of the exposure profile. Using the same mathematical model, the well-mixed room model, described in the previous slide, we can apply a probabilistic approach with the input values defined as ranges or distributions instead of single-value point estimates. Then, running multiple iterations of the calculations in which values are randomly selected from these ranges or distributions, a distribution of outputs is created. In the figure shown on the right side of this slide, we see the graphical output of this model simulation, showing several different fractions of the exposure distribution, including the 95th percentile output. Using a probabilistic approach allows for greater transparency about the variability and uncertainty associated with the model inputs. These models are available through the freeware IHMod 2.0. The benefit of modeling exposures is dependent upon the selection of the most appropriate models for the exposure scenario being assessed. The user must also be trained so they are competent to use the models and interpret the model's output. The learning curve increases with increasing model complexity. The models also rely on quality data to inform the algorithms. Quality data for model inputs tends to be limited, and this is the most significant barrier for applying the models. Evaluating the models requires quality exposure measurement data, which also tends to be sparse. Nevertheless, the models have been shown to produce accurate exposure estimates across a range of scenarios and are important tools for the exposure assessor. Inference is an approach that can be used to assess exposure. When guided by the right inputs and knowledge, it can be very helpful. For example, analogous or inference exposure data can be used where exposures are known for one chemical and the relationship between that chemical and another chemical are known. Then that relationship and data can be leveraged to estimate exposure for the other chemical that is used under the same level of controls. To illustrate this concept, we'll use the vapor hazard ratio, or VHR, to leverage data on cyclohexane exposures in a specific process area to estimate exposure to methyl ethyl ketone in the same process area. The VHR is the ratio of the vapor pressure of the chemical, expressed in millimeters of mercury, to the occupational exposure limit. In this example, we'll use the ACGIH threshold limit value, or TLVs, as the reference exposure limits. Consider a plant where the exposure of cyclohexane is known to be 25 parts per million in a specific process area. If the plant would like to use methyl ethyl ketone, or MEK, in its process area instead of cyclohexane, what will the MEK exposure level be? We can answer this question by completing the following steps. First, we estimate the ratio of the VHRs for MEK to cyclohexane by calculating the VHR for each chemical and then calculating the ratio of the two VHRs. Cyclohexane has a vapor pressure at 25 degrees C of 96.9 millimeters of mercury and a TLV equal to 100 parts per million. Therefore, the vapor hazard ratio for cyclohexane is equal to 96.9 millimeters of mercury divided by 100 parts per million, which equals 0.96. MEK has a vapor pressure at 25 degrees C equal to 86.7 millimeters of mercury, and its TLV is 200 parts per million. Its VHR, therefore, is 0.42. The ratio of MEK's VHR to cyclohexane's VHR is equal to 0.42 divided by 0.96, which is equal to 0.44. Next, we calculate cyclohexane's exposure as a percent of its TLV. Since the TLV is 100 parts per million, this works out to 25 divided by 100, or 25%. Next, we calculate the percent of MEK's TLV using the cyclohexane TLV expressed as a percent and the VHR ratio that we calculated earlier. So this is equal to 25% times the ratio of the VHRs, which was 0.42 divided by 0.96, which equals 10.9%. 10.9% of 200 parts per million, which is MEK's TLV, is 21.9 parts per million. So this is MEK's expected exposure level. So you can see how leveraging the analogous data, in this case cyclohexane exposure data, we can infer MEK's exposure level. The AIHA defines professional judgment as the application and appropriate use of knowledge gained from the formal education, experience, experimentation, inference, and analogy. It's the capacity of an experienced professional to draw correct inferences from incomplete quantitative data, frequently on the basis of observations, analogy, and intuition. Professional judgment is an essential element of the decision-making process. When informed by appropriate inputs, it can be very accurate. Proper use of the tools and approaches described earlier in this presentation weight the likelihood toward better decision-making and professional judgment. Drawing correct inferences requires access to relevant, high-quality data and information. Inferences made without these inputs may be unreliable, potentially leaving the workers at risk of being overexposed and underprotected. Drawing inferences and forming professional judgments are sensitive to the approaches used. When systematic approaches coupled with relevant objective inputs are used, the outcomes are much more likely to be accurate. Training in these domains is available, but hygienists need to be aware of the limitations and to seek out this training. In industries that have complex processes and many chemicals, such as raw materials, intermediates, products and byproducts, waste, support agents such as catalysts or maintenance chemicals, a facility may have dozens of exposure groups that include large numbers of chemical agents. This results in the need to assess hundreds or even thousands of exposure scenarios. A screening level assessment can be applied to determine if exposures are likely insignificant or potentially significant, where potentially significant requires a need for a more rigorous evaluation. Parameters that may be used in a screening level assessment may be health hazard rating, physical properties such as vapor pressure, the likelihood of becoming airborne, general or mechanical ventilation, etc. The decision algorithm should be simple, resulting in a decision in a matter of seconds. Qualitative assessments can be useful for prioritizing follow-up and allocation of resources. This type of categorization may be useful to set priorities, but it does not provide an estimate of the significance of exposure. For example, at a specific facility, all the high exposures are likely higher than the low ratings, but still may be well below exposure levels considered to be unacceptable. Qualitative assessments may be based on the physical and chemical properties of the chemical agents involved and their health effects, with consideration of the nature of the tasks that are or will be performed. With semi-quantitative assessments, exposures are classified into ranges, such as those used with the ECC or EIC ratings. These types of assessments can support compliance determinations or the determination of relative risk. They do not support quantitative risk. Note that there are cases where the categorization is based on assignment of exposures to a range based on a quantitative exposure estimate, and therefore that case would be a quantitative exposure assessment. A quantitative exposure assessment outcome is the assignment of a numerical estimate of exposure. There are a number of approaches to obtain a quantitative exposure estimate, including the collection of a data set of sufficient number of exposure measurements that are representative of the actual exposure distribution encountered by workers and analyzed using robust statistical methods. Exposure estimates based on determinants of exposure using an algorithm that has been evaluated and calibrated with rigorous data sets. Using mathematical models based on chemical and physical properties of the agent and fluid dynamics that have been evaluated and calibrated with rigorous data sets. Or using direct reading monitoring data, providing correlation studies have been conducted in situations where both personal and direct rating measurements are available for the same exposure scenario. In summary, there are several approaches to assessing exposures, each with strengths and limitations. Familiarity with all these approaches and their recommended application is important to ensure they are used appropriately and efficiently.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.